I have here a piece of the material that I hope to build the MV Dodgy Roger 2 out of. As you can see, it bends very easily, and it's also very lightweight. The bending is going to be great when I'm trying to form the shape of the boat, but once I actually have the shape of the hull there, I need some way to make it stiff. Right now I could very easily just snap this in half. So how am I going to make this foam stiff? For that, we must understand the sandwich theory. It's very easy for me to bend this paperback book into an arch. After all, it's just made of paper. But let's see what happens if I was to clamp this edge opposite the binding. With the edge clamped, it's now much more difficult for me to bend this book. If we look at the unclamped book again, we'll notice that the inside of the arch, the path that we have to follow, is a lot shorter than the path along the outside of the arch. So when we clamped this edge together and then we tried to fold it, the only way that was going to happen is if the top cover got longer or the inside cover got shorter. So while paper bends easily, it doesn't want to stretch or shrink. So for the boat, after I've bent it into shape, I'm going to need to attach skins to both sides, the inside and the outside, that will hold it into shape. The combination will have a higher stiffness to weight ratio than an equivalent hull made from only skin material or only the foam. Most boats these days use fiberglass for the skins. The fiberglass is glued to the core using a polyester resin. However, these materials are expensive and toxic to work with. Plus, the polyester resin would eat right through the XPS foam. So instead, I'm going to use cotton canvas for my skin and non-toxic Titebond 2 premium wood glue to glue the canvas to the foam. So what I don't know is how much stiffness the canvas and the wood glue are going to add to this. So let's do some science. So I've placed the foam piece here between two bricks that are 36 inches apart and measured the halfway point. I have here a box full of 80 quarters. So there's 80 quarters in a pound, so this box weighs approximately a pound. So what I'm going to do is measure the deflection when I place this box in the center of the beam. So let me start by measuring its nominal height from the table. So I have 3.771, so 3.771 inches. And then we will place this right in the center. And this is now at 2.659. So there's a bit of a curve in this, so I'm going to flip it over and do the same measurements with it facing the other direction. So we have 3.830, and with our weight on here, we have 2.848. All right, so we got the measurement, so now we just got to do a little math. So what we actually measured was the deflection of the beam. When we had the first side up, it deflected 1.112 inches. When we flipped it over, it deflected 0.982 inches. So we'll just take the average of those and say that our deflection was 1.047 inches. Next, we need to calculate a funny value called the moment of inertia. This is simply the width of the piece of foam times its height cubed divided by 12. Why it's those numbers, we're not going to get into today, but the answer is 0.4375 inches to the fourth. Finally, we're going to use those values to calculate the Young's modulus, or the modulus of elasticity. So this is the value that's going to tell us how bendy the material is. once again, it's another crazy formula. So the Young's modulus is the force that we are applying downward at the center of the beam, so 1 pound, times the length of the beam, which was 36 inches, divided by 48 times the moment of inertia, times the amount of deflection that we measured. So if we plug in all of those values from above, we find out that our modulus of elasticity is 2,122 pounds per square inch. So in the next segment, we will apply the canvas and the glue to the beam, let it dry, and we'll redo these calculations. After we've done the calculations, we'll be able to see how stiff it is in comparison to the untreated foam.